Good day, I'm Norman Wildberger. In today's video we're going to look at the projective line and metrical structure on it in yet a different way. We're going to extend the understanding of what geometry in this one-dimensional setting means to include not just the familiar Euclidean kind of orientation, but also a relativistic orientation, ultimately associated with Einstein's theory of special relativity. Okay, it's a very interesting story here, and it really opens up our eyes, I think, to a lot of new possibilities for what geometry is and the various kinds of investigations that we can make. We have to be prepared that our intuition that has been developed very steadily in one direction is really only oriented in one direction. There are many other vistas where things look quite different, but ultimately just as valid as the one that we're familiar with. Okay, it's a remarkable development in 20th century physics, the development of special relativity and then general relativity. And to a certain extent, modern pure mathematics hasn't really fully incorporated this understanding of the physicists into the sort of mathematical pure framework. And one of the reasons is that our reluctance to let go of the real number dreaming forces us to stay within a rather constrained alleyway when it comes to thinking about the possibilities for geometry. When we let go of that real number dreaming, we're no longer anchored down or tied down to real numbers. We can think more generally, and you'll see the advantages very clearly in today's lecture. Okay, so we're talking about the ordinary projective line with projective 1 points, just proportions enclosed in square brackets as usual. And here is the Euclidean structure that we've talked about quite a lot, where you basically introduce a notion of projective quadrants into this situation, allowing you to assign a number to a pair of lines. And here's the standard formula, and here's an alternate formula for it. Okay. And prominently, the denominators here involve these expressions x1 squared plus y1 squared. We take the sum of the squares of these two components and take products of those. And you might well ask, well, why do we do that? Why do we take the sum of the squares and not, say, the difference between the squares? Or this one squared minus 5 times that one squared? The main requirement that we do need is that the whole expression be homogeneous, but there's in fact quite a lot of different ways of arranging that homogeneity. So why did we pick this particular one out of the various possibilities that we could have had in front of us? Well, you can argue and say, well, this is the most simplest, and that certainly has some validity. But we'll see that this alternate form here is really equally interesting. Okay, so this is a new kind of relativistic structure as opposed to what we'll call a Euclidean structure over here. Okay, this relativistic structure is imposed by a new type of projective quadrants. So the quadrants between x1 to y1 and x2 to y2 is minus x1 y2 minus x2 y1 squared all over x1 squared minus y1 squared times x2 squared minus y2 squared. It looks just like this one, except that there's minus signs down here, and there's also a minus sign out front. Now it'll turn out, as we'll see, that this same expression can also be written as 1 minus this expression, x1, x2 minus y1, y2 squared, over again the same denominator, x1 squared minus y1 squared times x2 squared minus y2 squared. So this kind of situation over here, we've already had a look at some examples. The kinds of projective quadrants that we get are things like 4/5 or 1/2 or 9/10 in this case here. Let's have a look at the same lines, the lines 3, 1, 1, 2, and 1 to minus 1 over here. 3 to 1, 1 to 2, 1 to minus 1. So the objects themselves are the same, just the way we're going to measure their separation is different. Alright, so let's have a look at this new projective quadrants between these two 1 points, between 3, 1 and 1, 2. Well, in this form here, we would take the x1, y2 minus x2, y1. So 1 times 1 minus 2 times 3, so that's minus 5, and square it. It'll be a 25 up in the numerator there. There's also a minus sign here. And then in the denominator we would get 1 squared minus 2 squared, which is minus 3. And we would also get 3 squared minus 1 squared, which is 9 minus 1 is 8. So in the denominator here we get a minus 3 and an 8. The minus sign would cancel with that minus sign. And so we get 25 over 24. That is the projective quadrants between these two lines in this relativistic setting. Sometimes I refer to this relativistic setting as red geometry. In that same context, the familiar Euclidean one is blue geometry. And that's an aspect of chromogeometry which we are going to meet pretty soon. What about this other line here? This is quite interesting, the one that's in red. The line 1 to minus 1. What's the projective quadrants between this one and this one? Well, if you look at the expression, you'll see that there's a slight problem. And the problem is because when we look at this denominator here, this squared minus this squared is 0. Right? So if this line is involved, then one of the factors down here in the denominator is 0. So we're dividing by 0, which is not really allowed in our arithmetic. That means that the projective quadrants between any line and this particular line is not defined. This is a new phenomena that's going to play a very important role in this relativistic setting and really distinguishes it in a major way from the usual familiar situation over here. But in fact is not all that much different from the phenomena that we saw over here in an appropriate finite field. Our formulas for the Euclidean projective quadrants relied heavily on a fabulous identity, which I call it Fibonacci's identity, but I also suggested that it also goes back to Diophantus about a millennium before Fibonacci. And this was the identity here. And there's a variant of that, which is obtained from this one by replacing, say, y1 with minus y1. In which case this becomes a minus sign, this becomes a plus sign, and the minus sign here doesn't affect the right-hand side. So this is a variant of Fibonacci's identity. This one perhaps is more familiar if you're thinking in the terms of complex numbers. It represents the fact that the quadrants of a product of two complex numbers is the product of their quadrants. So now I want to introduce another variant of this identity, which we'll call the relativistic Fibonacci's identity. And here it is here. It's different. It's x1, x2 minus y1, y2 squared minus x1, y2 minus x2, y1 squared equals x1 squared minus y1 squared times x2 squared minus y2 squared. Okay, it's an exercise. Please check this directly by expanding out both sides and just seeing that there's some cancellation, otherwise they're the same. Another way of seeing this is to use a little bit of complex number kind of thinking and to take the first equation here and replace both y1 and y2 with I times y1 and I times y2, where I is some symbol that satisfies I squared equals minus 1. If we replace both of these with I times themselves, then the product of those two i's is a minus sign. The i's that appear here and here are common, and when we square that I, will come out front with a minus sign. And the I that we multiply this thing with gives us a minus sign, and the I that we multiply this thing with gives us a minus sign. So algebraically, this and this are just related by a relatively simple change involving this mysterious imaginary number I. But you don't need to think about i's. You can just think of it as a purely rational identity that you can just check directly by expanding out both sides. And please do that to make sure that you've checked this relativistic version of Fibonacci's identity. It's this identity that allows us to see that we have these two forms of this relativistic quadrants. So one of them was obtained by looking at minus this thing squared divided by the right-hand side. So if you imagine dividing everything by the right-hand side, then one of the terms you're going to get is minus this thing squared divided by these two factors. On the right-hand side, you will have 1. And over here, you'll have this thing squared divided by this product. So if we want to get this thing by itself, we can bring this to the other side. And so we see that minus this thing squared divided by these two things is 1 minus this thing squared over those two things. So that justifies that identity that I wrote down on the previous slide when we introduced the relativistic quadrants. A remarkable aspect of this relativistic geometry is that there are null points, something that we don't see in Euclidean geometry over the rational numbers. A null point is a projective one point, say a equals x to y, for which x squared minus y squared is 0. And we've seen that if either a1 or a2 is null, then the quadrants between a1 and a2 is not defined because a 0 ends up in the denominator. It's a basic fact that there are exactly two null points, namely 1 to 1 and 1 to minus 1. It's a bit of an exercise just to check for yourself that if you have a null point, that it's basically a multiple of this one or a multiple of this one. These are the only two null points that are around. And visually, these null points are these two lines here in red, prominently sort of perpendicular to each other in the usual sense, but not in the relativistic sense. And they form this cross, which is a sort of a two-dimensional version of what the physicists call the light cone. So in special relativity, the motion of photons is represented by a light cone, and this is sort of the two-dimensional or maybe even one-dimensional version of that. So it turns out this geometry is very, very important for physics, for modern physics. Even this one-dimensional situation has a major significance to physicists. Okay. So quite an interesting new aspect to this geometry, the fact that there are these two special lines in the geometry that are sort of God-given and they are special. Let's talk about perpendicularity in this relativistic projective setting. We denote perpendicularity with this familiar symbol. A1 is perpendicular to A2. And how do we define that? Well, I remind you that in the Euclidean case, perpendicularity between two such points was defined in terms of their quadrants being equal to 1. And that turned out to be equivalent, because of that second formula for the projective quadrants, to the condition that x1, x2 plus y1, y2 equals 0. Sometimes called the dot product or the inner product between these two vectors in two-dimensional geometry. So in the red or relativistic geometry that we're talking about now, we will proceed in a similar way, but we'll define A1 and A2 to be perpendicular precisely when x1, x2 minus y1, y2 equals 0. This is the relativistic version of this thing. It's kind of a relativistic dot product or inner product that's floating around here. So for example, the 1 points 1 to 3 and 3 to 1 are perpendicular, and written this way, because 1 times 3 minus 3 times 1 is 0. And it's pretty clear what the pattern is. Whenever you have A to B and B to A, then they are going to be perpendicular. Okay, as an exercise, please show that if you do have perpendicular points, and if the quadrant is defined, then that quadrant is necessarily equal to 1. So it would be almost the same as just using this as the definition, except that then the notion of perpendicularity wouldn't apply to null points. And it is useful to have the notion of perpendicularity apply to null points because of this next exercise, that the null points satisfy that they are perpendicular to themselves. So A plus is perpendicular to A plus, and A minus is perpendicular to A minus. This is a foreign concept in Euclidean geometry. There's no such thing as a vector perpendicular to itself unless it's the zero vector. But here we have these two lines which are perpendicular to themselves. This relativistic geometry is exotic but surprisingly important, because our world, the one that we live in according to the modern physicists, is actually geometrically more relativistic than it is Euclidean, at least when you look at it in a very large scale point of view. That's not so obvious to us because we're relatively small and relatively slow, but sort of from a large scale point of view, Einstein's special theory of relativity explains what's going on geometrically better than Euclidean geometry. So there's much to be gained by getting some experience, even though this is just a very modest relativistic geometry. It's really just only still a one-dimensional situation. But it's the one-dimensional situation which is sort of at the core of a lot of higher dimensional relativistic phenomena. So if you're a physicist, this is a great place to start learning some modern geometry. So let's have a look by staring at a few examples. Say some lines, line 3 to 1, the line 1 to 2, line 2 to minus 3. Those are three lines we can find quadrances between them just to see what they look like. And then here are the reference null lines, A plus and A minus. We're not going to use them to compute quadrances because we know then we get denominators which are 0, which is not allowed. Okay, the quadrants between 1 to 2 and 3 to 1, we've calculated that before. That's 25 over 24. The quadrants between 1, 2 and 2 to minus 3. Okay, let's use this form of things. So 1 minus the dot product 1 times 2 minus 2 times minus 3 all squared over 1 squared minus 2 squared times 2 squared minus minus 3 squared. Okay, so here there's a 2 plus 6, that's a total of 8, so 64. And over here we have a minus 3 and a minus 5 for a total of 15. So we have 1 minus 64 over 15, which is minus 49 over 15. And you can check similarly that the quadrants between 3 to 1 and 2 to minus 3, this one here, is 121 over 40. Okay, now another exercise. Check that the spread function, which is basically the embodiment of the projective triple quad formula, applies to these three numbers. That these three numbers satisfy the projective triple quad formula. This is what we would expect if we were in a Euclidean situation and these were Euclidean projective quadrances, but now it appears that, at least in this case, these three also satisfy the projective triple quad formula. The exact same projective triple quad formula. No difference at all. It's very interesting and suggestive possibility. So I can't stress enough that if you're an amateur mathematician and you're looking around for something to investigate, to make some discoveries of your own, this is a really great direction. To think about geometry in these different contexts, especially in a relativistic context. This is a situation which has unfortunately been a blind spot for 20th century mathematics. Some people have worked in this direction, but not as many as really should have. Okay, there really has been all these opportunities of pushing geometry forwards in a relativistic setting. And I'm talking about classical geometry, not differential geometry. Classical, triangle geometry, circle geometry, conic geometry, and so on. All these things in a relativistic setting. Huge opportunities. So a good way of starting is to use this opportunity right here to get familiar with the essential workings of these kinds of geometries. And to do that, I'm going to give you some exercises. So these are relatively routine. They basically follow similar patterns that we've already talked about in the Euclidean case. So there's nothing conceptually too dramatically different, but it's very instructive to work your way through them And it will be surprising to you that things work out as pleasantly as they do. You ought to be surprised. You ought to be thinking, wow, why hasn't anybody told me about this before? Very good question. Well, one of the reasons really is because people haven't understood rational trigonometry before. Okay, it's a relatively new development. And it really underlies a lot of this thinking. That we can think rationally and algebraically about a lot of things which formerly people thought you needed analysis. But you don't need analysis. You just need algebra and the right way of thinking. Okay, so here's another exercise. Show that in this red relativistic geometry, any projective quadrants, Q say, has the property that it's either less than or equal to 0 or it's greater than or equal to 1. This is assuming we're working over the rational numbers. So this is exactly complementary to the situation in the Euclidean situation. In the Euclidean situation, a projective quadrant was always in the range 0 to 1. Here in this red relativistic setting, it's exactly the complement of that. It's quite interesting. The next exercise is suggested by that previous example. I want you to show that the projective triple quad formula holds without any alteration in this relativistic projective setting. And this result, another exercise, very important, very useful fact, that if you have three numbers, Q1, Q2, and Q3, which satisfy the projective triple quad formula, in other words, S of them is 0, and if one of them equals 1, say Q3 equals 1, then the other two sum to 1. Right, so if you have three numbers and one of them is 1, they satisfy the triple quad formula, the projective one, then the other two sum to 1. In particular, if you have two projective 1 points which are perpendicular, then any other one will form two quadrances which sum to 1. So three very interesting and important exercises. All right, so the basic philosophy is that pretty well everything that's valid in the Euclidean setting is likely to be valid in this relativistic setting if we organize things the right way, if we look at things in the right way. So the rotations and reflections that we were talking about in the Euclidean setting have analogs in this relativistic setting. And they become quite important in relativistic physics. Okay, so the rotations first. We'll denote them with exactly the same kind of symbol, a row. They're labeled also by a projective 1 point, say A to B. And this symbol is defined, first of all, just in terms of its combination with a projective 1 point x to y. So we just define this symbol in terms of this product equaling this. And this is, in this case, ax plus by to bx plus ay. Exactly the same as in the Euclidean setting, except that there's a plus sign there in that first expression rather than a minus sign. And the reflections, well, same kind of thing. They're given by sigma a to b. And the formula is very much the same as it was in the Euclidean situation. It's ax minus by to bx minus ay, which is just the same as it was in the Euclidean setting, except that there's a minus sign here where there used to be a plus sign. In matrix form, you can think about these as transformations, as projective transformations. We'll talk about what that means more precisely some future point. But in any case, these 2 by 2 matrix A, B, B, A represents this relativistic rotation. And the relativistic reflection is represented by the matrix A minus B, B minus A. And what did we do with our rotations in the Euclidean setting? Well, we realized that we could sort of compose them. We could take a projective 1 point and apply one rotation, and then we could apply another rotation to that. And that turned out to be what you got when you took the same 1 point and applied a different rotation. one given by some new 1 point, which is in some sense some combination of the two original 1 points. So this defines a algebra structure on the projective rotations. And here's the crucial way that we compose these things, and you can check this, that A to B times C to D is AC plus BD to AD plus BC. Very much like the complex number story, with a small difference that there's a plus sign here and not a minus sign. So please check that this actually gives an associative commutative multiplication which has an identity. The identity is 1 to 0, just as it was before. But it's not complex numbers, so it's some kind of analog of the complex numbers that's more suited for relativistic work. So is there such a thing? Well, yes, there is, and it's quite useful for physicists. So again, we see we're going to have to expand our thinking in yet another direction, that not just complex numbers are around to help us in two-dimensional geometry, but also these well-read kind of complex numbers are around to help us perhaps in red geometry in 2 dimensions. So very intriguing possibility sort of in this direction, suggested by this algebraic structure in this one-dimensional relativistic situation. Okay, and now paralleling a result that we had in the Euclidean setting is this theorem that if A to B is a non-null projective point, which means that A squared plus B squared does not equal 0, then both rho A to B and sigma A to B are isometries. What that means is that if we have two projective 1 points, say P1 and P2, and we take the quadrants between them, that's the same as what we get when we take the quadrants between the 2 points that we get by multiplying both of them by, say, rho, this being rho. And it's also the same as what we get when we take the quadrants between what we get when we multiply these 2 points both by sigma, this being sigma. This is the condition of being an isometry. And note that it's important, in fact, to require this condition. Please investigate what happens if A to B is a null point. What does rho A to B and sigma A to B do when you're multiplying points by those? Okay. It's something a little bit different that we don't see in Euclidean geometry. All right, so please prove this. And then you can construct an analog of an exercise that we did in the Euclidean case, which is to list the various multiplications that exist between the rhos and the sigmas. So rho A to B times rho C to D is rho AC plus BD to AD plus BC. We've seen that formula in the previous slide. But you can also multiply a rho by a sigma or a sigma by rho. In each case you get a sigma. And here are the various formulas. And you can also multiply 2 sigmas and you get a rho, and here's the corresponding formula. And these formulas are well worth staring at. They're kind of pleasant and pretty, and they compare pleasantly with the formulas that we got in the Euclidean case. So a whole new world of potential geometry opening up here, still just in this one-dimensional case. But the story really isn't complete. So I'm obliged to sort of close a circle of ideas here by telling you that there's actually a third geometry floating around. And it's kind of implicit in these formulas, perhaps a little bit. So there's a third geometry floating around here, still in this one-dimensional situation, which is what I call the green geometry. Okay, and it's also another relativistic geometry, and sort of plays a complementary role to the red relativistic geometry. But the whole story really sort of comes forth and comes really alive when we think of all three geometries together at the same time, interacting. When we have our pizza with not just pepperoni, not just mushrooms, but pepperoni, mushrooms, and onions all at the same time. A very rich meal. Very satisfying for anybody with an interest in geometry. So next time I'm going to introduce you to another way of thinking about relativistic geometry and this remarkable threefold symmetry called chromogeometry. I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.